All right, this is a video for the remaining problems from section 5.5/5.6 from our notes today. We did kind of one of every type, but we needed to cover some variety. So section 5.5, 5.6, 3, part A. This was a solving equation where we have logarithms in our equation. When you have logs on all of the pieces in your equation, you want to try to get one log on each side. So because of the property that says if two logs have the same base, so this one right here and this one right here, and there's addition between them, we can turn it into one log with that base and multiplication between the inside of the argument. So that would make this log 4 of 3x plus 2 equals log 4 of 15. And then because we have the same log on each side, we set the insides equal. So 3x plus 2 equals 15. We would subtract the 2 and divide by 3. So we think the solution is 13 over 3. You need to double check that 3x plus 2, since that one has an x, 5 and 3 are both just numbers, so they're already greater than 0, but 3x plus 2 has to be greater than 0. So if you do 3 times 13 over 3, that would just be 13, plus 2 is 15, so that's greater than 0. So that solution does work. For C part, again, we can use the fact that plus between two logs that have the same base. So this is natural log, which is base E. So this would become natural log of x times x plus 6. So we turn that into times between the two arguments. On this one, this is a coefficient, so that can be put back on here as a power. So that's going to be natural log of 9 to the 1/2. This is natural log of x squared plus 6x if we distribute. And this will turn into square root of 9, which would be just 3. And since we have a log that matches the same base on each side, we set the insides equal. We would need to move the 3 over. And this one does not factor, so we will need to use quadratic formula to find the solutions. So x equals negative b plus or minus square root b squared minus 4ac all over 2a. That is a negative 3, by the way. This would be 36 plus 12. So this is negative 6 plus or minus the square root of 48 all over 2. 48 does have perfect squares that go into it, specifically 16. So that would be 4 on the square root of 3, because square root of 16 is 4, and then times 3 would make the 48. And then we can divide everything by 2. So x equals negative 6 plus, negative 3. Negative 3 plus 2 square root of 3. Or negative 3 minus 2 square root of 3. So I'm just going to separate that. These are the two possible solutions. You need to check. X needs to be greater than 0 and x plus 6 needs to be greater than 0. This second case down here has to be a no. Those are both negative, so if you plug a negative into that very first spot, it will not be greater than 0. But let's see what is the decimal for negative 3 plus 2 square root of 3. So 2 times the square root of 3 is 3.46 and change. And then we have to subtract 3 from that, just kind of working backwards. So that's 0.46. So 0.46 is definitely greater than 0, and 0.46 plus 6 is greater than 0. So the only solution to this one is x equals negative 3 plus 2 square root of 3. Now, typically we wouldn't give you one on a test that has such a far, difficult solution to check, but just to let you know that that could happen in an example. So let's look at E, because we did D in class. On this one, notice not everything has a log, so we have to get all the logs on one side and the non-log on the other side. So we would subtract over the log of x minus 2, since it has a plus in front of it. And this would then be equal to 2. We would convert this to now being one log by changing it to division between the arguments, because subtraction turns into division using our law of logarithms. And then this one's a little harder for people to solve. You can't set this equal to 2. There's not a log on the right side. So you have to think, oh, this is base 10. We have to convert this using the spiral technique. So if there's ever a number that doesn't have a log on it, you're going to end up having to do this technique. So 10 squared equals the 57x over x minus 2. That's 100 over 1 equals 57x over x minus 2. Cross multiply, we get 100x minus 200 equals 57x. Subtract the 100 over, that's going to be negative 43x. Divide by negative 43. So this is going to be 200 over 43. Now we need to double check. 57 times 200 divided by 43, everything's going to be positive, so that'll be okay. And as long as 200 divided by 43 is bigger than 2, which it is, minusing 2 will still be positive. So this solution does work. And then for f, again, we have something that doesn't have a log on it, so we're going to get everything away from it and try to combine the logs on the left side. So this again is going to be division. So x over x plus 1 equals 1. This is a base e. Remember, that's kind of hidden there. So since there's not a log on both sides, we have to use the spiral technique. So e to the first equals x over x plus 1. So this would be over 1. So this will be ex plus e equals x. We're trying to solve for x, so we need to get the x terms on the same side. Then factor out the x over there. And then we would divide, so this is e divided by 1 minus e. Now that's the exact solution. To help you check this and see if it works or not, you need to type it in and get a decimal. So this is e, which would be e to the first, divided by parentheses 1 minus e to the first, close parentheses, hit enter. This is negative 1.58-ish. Now, if you plug that into the very first one, that will not let that be greater than 0. So this is actually a solution that doesn't work. It's the only solution we have, so that means this is a no solution equation. Okay, for number 4, we're just supposed to use the change of base formula to help us find the exact, well, first of all, find the exact solution and then use change of base to get the approximation. This is just taking the log of both sides. That's one way to solve this, because then we'll be able to pull the power to the front. So pull the power on that x to the front of that log, and then we isolate by dividing the log 4 over. So this is the exact solution. The approximation you find by doing this on your calculator. So log 3 divided by log of 4 is 0.79. So approximately 0.79. This one we're just using change of base only. Change of base says if you have a base that's not on your calculator, so 2 or 5 or something like that, you can change it to base 10 or base e by always using the top argument is going to be the original argument, and the bottom argument is going to be the original base. So log 20 divided by log 2. So I'm using base 10. So log 20 divided by log of 2 is 4.32. For 6, you're working the change of base formula backwards. Notice these both have base 7. But if we wanted to convert it backwards, we could make this log, and then you have a base and an argument. The top one is the original argument. The bottom one, remember, is the original base. Now, the reason we would want to do this is that 243 is 3 to a power. So if you think about setting this equal, and says do not use a calculator, so set this equal to x. Let's try to solve this. So 3 to the x equals 243. If we can get these to have the same base on each side, we can solve it. So let's see, 3 to the 5th power is 243. So that means that x has to equal 5. Okay, we did 7a in class. We're going to do 7b. This is having us try to solve for x, and there's multiple bases involved that have x in them. So the quickest way to get this solved is to take the log of both sides so you can pull the powers to the front using that law of logarithms. So if we pull this power to the front, this will be 2 minus 3x times just a log 3. And this will be 2x plus 1 times a log 4. We will need to distribute the logs to each of these binomials. So this will be 2 log 3 minus 3x log 3. This will be 2x log 4 plus log 4. Okay, your next idea is to get the parts that have x on the same side together, and then the parts that don't have x go on the other side. So I'm going to add this 3x over. So 2x log 4 plus 3x log 3. This log of 4 is going to move to the left side, so this will be 2 log 3 minus log of 4. We would want to pull the x out of the common terms over here, and I'm also going to move my powers back up. I prefer having them not on the numbers here. So this would be 3 squared, so that's going to be log of 9 minus log of 4. I'm going to pull the x out, and then I'm going to have 2 log 4 means that the 2, just the 2, not the x, is going to go back on the 4. So that would be log of 16 plus the x has come out, and then this 3 is going to go back up here. So that's going to be 3 cubed, so that's going to be log of 27. So I'm just pulling the x out as a GCF, but also placing those powers back on just so that we have regular numbers and not numbers in front of our logs. Okay, so to get x by itself, we need to divide the log 16 plus log 27 to the other side. So this will be log 9 Sorry, give my computer a second. There we go. So log 9 minus log 4 divided by log 16 plus log 27 equals x. Now I'm actually okay with that if that's where you stop, but we could clean this up a little bit more. On top, because there's subtraction, that would become a division. On bottom, that's adding between them, so that's going to be multiplication. So 16 times 27 is 432. And then because they both have same base on top and bottom, if you wanted to, you could convert this to log of 432 as the base and 9/4 as the argument. So that is it for that one. And I would be okay with either of those solutions. Okay, for C, we're doing just another solving one. There is a 2 here that doesn't have a log, so we're going to leave it on the right side. So this would be log of 5x plus 1 minus log of 2x minus 3 equals 2. And then we would make this into division because of the subtraction sign. If it was a plus sign between the two logs, you would FOIL this out. But it's a minus sign. And then we have to convert this because there's no log on the other side. So this is going to be 10 because it's base 10. So that's going to be 100 equals 5x plus 1 over 2x minus 3. Cross multiply. We get 200x minus 300 equals 5x plus 1. Subtract that, that'll be 195x. Add the 300 to be 301. I'm getting 301 divided by 195. Now, as long as each of those turn out to be positive, we're good, and I believe that they will. So this is going to be the correct solution for that. Okay, and then the final one we need to do together on the video is number 8. Use the compound interest formula to determine how long it will take a sum of money to double if it's invested at 0.06 or 6% compounded monthly. So we're using the formula that allows us to talk about compounding in certain periods, which is P times 1 plus R over N to the NT. We don't care how much money you have. All we care about is how long does it take for that money to double. So you could just randomly pick amount for P. It could be 100. Doubling would mean that you now have 2 times 100 or 200. So this would be 200 equals 100, and then 1 plus 0.06 divided by 12 to the 12t. So notice what we're solving for is actually an exponent, so we're going to have to use a log. I would divide the 100 over first, just to isolate this big old base right here. And then if it was me, I would just take a log of both sides. That way we can pull the 12t to the front. So log of 2 equals 12t times log of this big fraction, which you'll just leave as a fraction for right now. And then to get t by itself, you need to divide by not only the log part, but also the number 12. So t equals log of 2 divided by a 12 and a log of 1 plus 0.06 divided by 12. So we need to type all of that in on our calculator to get an estimate, because you're not going to give that someone an amount of time in logs. So 2 log divided by, open a parentheses, 12 times, I'm going to open another parentheses for my base of my log, or my argument, so 1 plus 0.06 divided by 12, close that, make it a log, and then close the bottom parentheses. So I'm getting 11.58. So T is 11.58 years. So if this person wants their money to double, it's going to take them almost 11.6 years to make that happen. Okay, and that's the end of the video.